Amazing. Okay.
Okay, so I will begin. Um, okay. So like as I promised, I'm not going to talk like at too many like hi-fi things. I'm going to make it a fun class, and I'm going to look at more of the geometric side or the geometric flavor of complex analysis like towards the end, and like geometric function theory. Um, so okay, like once again, if you feel free to speak out, or else I won't be looking at the chat that frequently. So please do that. Okay. So first things first, whenever we are doing analysis on something, we look at some nice things such as limits, open sets, and in general, like how the topology of the whole thing works, right? We need to have like the setup in order to be able to work and think about stuff, the interesting things properly and truly capture the behavior of things. So I shall begin off with the spirit of analysis, which is with these two definitions, with limits and open sets basically. Okay, so how do we define a limit, right? um, Limit is basically, let's say, first I shall define the limit of a sequence, and then get into the limit of a general function. So basically what you want is that, let's say this is the complex plane. So this probably denotes x, this denotes y. So this point is x plus y somewhere in here. So what limit means is that, let's say you have points a1, a2, a3, and so on. They come together and they seem to converge at some point, right? So how do we really formalize this notion of a limit, or the limit of a sequence, right? What does this mean? So we all know, so many of you would probably know this. So what we do is that we define the limit in the following way. First, we take the point L, which we call the limit point, and what we draw is a circle of a given radius, let's say epsilon. So what we claim is that this limit an goes to L if, for all, like no matter how small you make this, no matter how small you make this circle around this limit point, like there will be infinitely many points within that circle. Or to be more precise, for all sufficiently small like epsilon, there exists an integer n such that for all n, okay, maybe I should change the notation a little bit. For there exists an integer n such that for all n greater than n, an minus L lies in this ball of radius epsilon, basically, or a circle of radius epsilon. So this really captures the definition of the concept that something converges, like the points move around, and towards the end, they seem to be getting closer and closer to a point. And once we define limit, next natural thing is to define an open set. So many of you would have seen the definition of an open set and would have feel like, okay, what is this complicated thing? So I will actually give a much more simpler definition of it. So whenever we have a set, I'm actually going to define the boundary of it. So what do we really mean by the boundary? Okay, let's take the complex plane once again. So if we have, let's say this is our set. So what do we mean when a point is on the boundary, right? So what we mean is that if we take a small circle around it, okay, seeing circles everywhere is kind of a common thing. So if we take a sufficiently small circle around that point, which we are claiming to be a point on the boundary, then a part of that circle, or the region within that circle, lies within the set, and a part of the part of the circle lies outside the set. So basically, if we were to draw, so in general, this is how we define the boundary of a set. So like if we take a point and we draw a circle around it, a part of that circle contains the set, contains points from the set, and some of the points are from outside the set as well. And we denote the boundary using this letter. Oops, sorry, that's the wrong letter. We denote the boundary using this symbol, basically. So what is an open set? It's actually nothing complicated. It is a set which does not have a boundary. Some of you might be confused that, okay, how is this the same as the definition that we learned? So I'll just get there. And for those who did not quite grasp or kind of fully understand the concept of boundary in the most rigorous setting, you can just imagine the boundary of a set, and open set is a set which does not have a boundary. So let me take a simple example of what a boundary would be. So for example, consider the set, oops, consider the set
Okay, like
S.
when you are drawing a boundary, you can even you can even put a point inside the set, and when you draw a circle around it, some part of the circle lies outside the set, but that's not a boundary. You are right.
Yes, so here's the key thing. The ball has to be sufficiently small. Thanks for pointing it out. I was kind of sloppy with the way I said. Okay, you're correct. Let's say we take a point here and we take this circle. There are points outside it. But if we make the circle sufficiently small, eventually there will be no points from outside. The same thing happens if we take a point from outside, right? Okay, if we draw the circle to be sufficiently big, then there are going to be points from within the set. But if we keep on making the circle smaller and smaller, what we find is that in this circle, as we keep on making it smaller, there will be no points from the set anymore. So does that, but in the case of the boundary, no matter how small we make the circle, just no matter how small, let it be 0 0.1, 0 0.001, no matter how small it be, there is always going to be points from within the set and from outside the set. Does that answer your question?
Yeah.
Okay. Thanks for pointing it out. I guess I was kind of sloppy with the with the way I defined the boundary. So we define, okay, so I'm now going to give an example of an open set. So basically we take all the points z such that the absolute value of z is less than some real number r. So what this basically means is that we have we have a set like this. So all the points inside are present, but once it crosses R or reaches R, there are there are no more there are no more points within the set. So why is the set an open set? Because the boundary of this set is nothing but the set of all points which have radius equal to R. And so this is the reason why it is an open set. So this is basically the definition that I'm giving of an open set. So is this definition of open set clear, or does anybody have any doubts? Feel
Can I
free
just
to.
repeat? Sorry, can I just repeat this point?
Okay, did you understand the concept of the boundary of a set?
Yeah, yeah.
Okay, so an open set, I'll just go to another slide. An open set, so this is basically the definition. If you take an open set S and you take the intersection of it with its, oops, that's the wrong symbol. And if you take the intersection of it with its boundary, it's the null set basically. So basically the open set does not contain its boundary. So all the points on the boundary of an open set lie outside it. Like for example, if you
Okay,
take
that's
S,
like the symbol of a boundary.
yes, yes, yes. This is the symbol of, this symbol denotes boundary. Yeah, so for example, if you take this example, the boundary is nothing but this, right? If you
Yes.
just visualize it, okay? And the intersection is the empty set. So this is, so why is open set so meaningful, right? Okay, so now I will get into the more topological sense of definition of an open set. In a more they're equivalent, so I gave this definition because this is much more easier to visualize, and I feel that when I originally studied open set it did not make any sense to me. So we claim, so this is an equivalent definition to the one that I gave before. I'm just going to, this is just, or you can think of it as another property of open sets basically, and this is really going to highlight why, um, this is really going to highlight why open sets are so interesting. So when we say open set in the context of, context of topology, what we mean is that if we take a set, and okay, maybe I should make the boundary dotted to indicate it's not within the set. If we take any point of the set, if we can actually find a sufficiently small circle or a sufficiently small ball which is centered around the point. For example, we can draw this. For example, if we take this point which is very close to the boundary, we can draw an even smaller circle which is entirely contained within the set. So if my definition isn't quite clear, I'll just write it down formally. Oh, what the heck? It's not going down. Oops. Uh, just give me a moment. Just some glitches happening. Okay, wait, let me rewrite it a little bit. Um, so what this is basically saying, to reiterate, it means that if you take a point, no matter where in the set, even if it is close to the boundary, we can always draw a sufficiently small circle around it, which is entirely contained within the set S. And if you think about it a little bit, you will see why the open set is the previous definition of the open set using boundaries is equivalent to this one. So I would not actually go into the full analysis rigorous proof. I think you can kind of visualize it, right? Or should I give the proof of why they're equivalent? Um, I'd prefer not to, but if I think you all can visualize it, or else I will go into giving the proof of it.
You can
Should I give?
visualize.
Okay, so I will. So I won't. You can try this out. It's a very simple exercise. It follows immediately from the definitions. So I'm not going to go into this, but keep this in mind. And this is the reason why open sets are so special. Okay. Okay. So now we come into the now I will demonstrate why open sets and limits and all these are so relevant. So
So
so now let's get.
it
Yes.
may
Yes.
be
Go
a
ahead.
like it may be a dumb doubt, but how is open set different from a infinite set?
Um. Open set. Okay. So some infinite sets are open sets. For example, the entirety of complex plane is an open set. So like they are they are not contradictory or anything, or they are not mutually exclusive or anything.
No,
So
but like are like if are they different? Because even infinite sets don't have boundary, I guess.
um if you, for example, okay, I'll give you an example of an infinite set which is actually not open. For example, let's say this is our complex plane, or at least some section of it. So what you do is that you take, okay, I'll just draw the, wait, I'll not draw the boundary of it. Okay, So let's say this is the grid x, y. Let's say, okay, we what we do is that we consider all points within this strip basically. Okay, so let's say this is minus a, this is a. So we consider all points inside this. Basically, we are considering the set z such that um, the real part of z um, is okay, the absolute value of the real part of z is less than equal to a. So this set is actually not open because the boundary is contained within this. If you see, this is the boundary, right? The line x equals a is the boundary of the set, and it is indeed contained within S. So this is indeed not an open set. This is in fact a closed set actually. So this is not an
So
open
like
set. So I guess that answers your question.
if I say that the number of real numbers between 0 to 1 is an open set, but is not an open set, but an infinite set, does it make sense?
The number of okay, so when you're saying numbers between 0 and 1, do you mean okay?
Real numbers,
Do you
yes.
mean the okay? You're I would not want to get into the real line actually right now. Like you can because in the case of the real line, you have to define the topology slightly differently. Uh,
Oh,
like it's similar. You can talk to me about this in the class, but basically the point is that infinite sets can be not open. Okay, I should write not open here. Why did I write open? This is not open set, not open set.
oh.
This is so infinite sets can be both open and closed. So infinite and open does not have any sort of like fundamental relation. So infinite open, they can be, it can be infinite and open, it can be infinite and closed. So that's so there's
Okay,
no
so some infinite. Okay, so some open sets can be finite also.
yes, yes, yes. Like I gave the example here, right? This is an open set because it does not contain the boundary, which is this.
Okay,
Does that make sense?
yes.
Okay. Okay, so just keep with you this picture in your head that open set is basically a set from which you have deleted the boundary. Okay, keep that image in your head. I think that intuition will really carry us forward. Okay, so
Uh,
now let's get
um,
into actually some of the yes,
uh, like how do like if you have a finite set instead a discrete set of points, what do you do then?
yes.
Like how do we define?
Okay, that's okay. If it's a discrete set,
Because like about
okay,
any point I can just like consider a very small ball and then no point
yeah,
inside.
okay. So yeah, so the discrete set itself, like the set itself, is its boundary in the case of a discrete set, and that wouldn't be an open set. No, that wouldn't be an open set. Okay, so some people are typing in the chat. Um, let me just see. Oops. Does it cover points inside the boundary? Nikhil, could you please elaborate? I'm sorry, I'm checking the chat a little bit late. If you're here, is Nikhil here? You can, or is your doubt answered? So, like, just to clarify, open sets does not include points inside the boundary. Like the points on the boundary do not belong to the open set. So put it in your head. An open set is a set from which you have forcibly deleted the boundary. Okay. So that's what it is. Okay, so just try to visualize, just keep this example in your head of this that I've given here. S is Z such that Z is less than R. So just keep this example in your head, and I think you should be completely fine. And if you're not kind of getting this, okay, this is too complicated, just okay, this is only for like bookkeeping purposes. For majority of the lecture, like for to get the bigger picture, you don't need the concept of open set. Just follow along. If you don't get it, it's fine. Try to capture the bigger picture. So because it is kind of slightly difficult if you're looking at this the first time. Okay, so let's now get into something more interesting. By the way, Mandar, did I answer your question or
Yeah, I couldn't really get why a discrete self is a boundary of itself.
Because if you take any point by wait, just Nikhil is just asking something. If we define the real part of the z to be less than a, is it an open set? Okay, see, z is, by if you mean z the set of integers. Okay, in the previous slide.
No, no.
Okay, here. Z. Oh, you meant like the complex numbers. Oops. Okay, this is not an open set, to be clear. But
No, he removes the equality sign then.
oh, okay, if you remove the equality sign, then yes, it is an open set. Okay, thanks for wait. Why is the oh shit? Why is the why is this thing not working? Okay, it's working now. Yes, if I were to remove this thing here, then it becomes open. Just to be clear, then it becomes open. But if the equality, so just to write it out, z such that real z, this is an open set. Okay, and Mandar, just when you're saying discrete set, do you mean points which do not have an accumulation point? Or okay, I won't even say that. Like you mean like random points, right?
Yeah.
Which are like randomly spaced. Like I'm not
Yes, yes.
speaking very rigorous language here, but I kind of get what you're saying. Okay, this is not an open set, because if you take any point here, and if you draw a circle around it, it's going to include this point itself and points outside, no matter how small the circle is, because we can't
Oh,
set the
so
radius, right? Does
oh,
that
so we
make sense?
oh yeah, yeah, we include the circle center. Sure.
Yes, yes, yes. Okay, I think you were talking about like the punctured ball, which is kind of common in analysis. So, but here we are not considering the punctured ball. It's the whole circle or the whole ball, not the punctured circle basically. Okay, let's get into the fun stuff now. It's already 20 minutes discussing this. Let's get into the real fun stuff. Okay, how do we define a derivative in the complex sense? By the way, I'll just check the chat once again just in case. Okay, Nikhil, I think I answered your question.
My
Okay.
idea for
der-
like finding derivative is like we take a very small open set around the point, and then we do the normal derivative thing, which is f of z plus epsilon minus f of z by epsilon, as the limit as epsilon tends to zero. But instead, we take it as like epsilon as a vector in the complex plane, something on those lines.
ye- yes, yes, yes. Okay, so yes, you're kind of having the right idea, but there are a lot of richness into when we're defining the derivative. Okay, so wait, let me actually define what it means to be uh, what it means to be the limit in the case of a function basically. um wait I'll just go to another slide. Okay, so what does it mean limit in the case of a function? What does this mean? Is it z tends to a? So what that basically means is that, let's say we take a point. Okay, let's say this is the complex plane, and let's say this is the point a. What we basically do is that we keep on drawing smaller and smaller circles around it, and we keep on taking points inside that smaller and smaller circle and see where that tends to basically. So I'm not going to give the full epsilon delta definition, but I guess you kind of see how that follows similarly from the limit definition in the case of a sequence. So or actually, if anybody wants, I can actually give it, but that's not going to matter that much if you kind of understand what limits is and you understand my previous definition in the case of sequence. So if anybody wants, please speak out. I'll give the full epsilon delta definition of limits in the case of function.
Okay, I didn't understand the intuition part of this. Like, can you just explain
Sure,
it?
sure. Okay. Okay, so in the case of a sequence, right, what do we have? We take points a1, a2, a3, and what we see is that they slowly spiral into some point, right? So we are trying to capture the similar thing in the case of the definition for z, in the case of f of z. So what we do is that, okay, so probably I should go take another slide actually to define the whole thing. So let's say this is the plane, and And let's say, okay, wait, I'll just erase that. Okay, I'll actually define two planes. One I'll call the z plane, and the other one I'll call the w plane. And how does the z plane transform into the w plane? So what we define is that we take a point z from the z plane and map it to the point w, which is defined as f of z. Okay, so in the left side we are seeing all the points on the complex plane, and on the right side we are seeing what happens to these points, like where the function maps these points on the complex plane basically. So I think this will actually help clear the definition. Okay, so when we say the limit of z tends to a of f of z is equal to, let's say, some w naught, what do we really mean by that? Okay, so we take some point a here and some on the z plane and some point w naught on the w plane, or the plane in which the function is getting mapped. So what we do is that we look at what happens when we take z is equal to, let's say, some point x1, z equal to some point x2, z is equal to some point x3, z is equal to some point x4, and as we keep on making z closer and closer to a, as the point is being coming closer and closer to a, we look at what happens to f of z. Okay, so what happens is that f of, let's say this is f of x1 and f of x2, let's say f of x3, f of x4, and if this limit indeed is this, if limit of z tends to a of f of z is indeed w of o, then what we will see is that this f of x1, f of x2, f of x3, all of them will slowly start tending towards w0. Does that make sense? um Aryan, does that
Yeah, yes.
okay, so if it's not clear, I can try perhaps giving the full definition. I think that if that would help actually. Do you want the full definition, or do you think you have kind of gotten the intuition?
Yeah, no, I've gotten the intuition.
See, basically there are two planes, the z plane and the w plane. And as we move z towards the point A, we look at what happens to f of z. So what we see is that f of z also moves to w0. So in that case, we define that limit of z tends to a of f of z is equal to w0. So here's one caveat, one subtlety to when we do this. Okay, let's suppose we were to take another path. Let's say, so this was one path to A that we took. Let's say we took another path, right, to A. So let's say this is some y1, y2, y3, y4, dot, 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 and it slowly goes towards A. In order for this, in order for this to be true, the limit of z tends to a of f of z is equal to w0, we would need to have that these f of y1, f of y2, f of y3, okay, let's say the points are here, 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 they must also tend to w0 basically. So this is what it means, like no matter which way you take while going towards a, f of z will also go only towards w0. It does not matter. It's kind of like the limit left hand side, limit right hand side, right? In the case of real numbers. If you have the real line, if you go towards the limit point from the right or from the left, the limit still remains the same. So that is basically the thing what I'm trying to say here. So like no matter how you go towards a, as no matter how you move z towards a as z is equal to x1, x2, or z is equal to y1, y2, or z across any path towards a, the f of z will also move only towards w0. So that is what it means. And when I originally said that these points tend towards the point, tends towards the limit, what I really meant was that um, let me just clarify it a little bit more. If you take this point on the z plane and this point on the w plane, if we keep on drawing sufficiently smaller and smaller circles from which we keep on taking points, right? Like if we keep on making smaller and smaller circles from which we pick our x1, x2, or y1, y2, that f of x1, x2, f of y1, y2 will also tend towards w basically. So if it's kind of not clear right now, it's fine. So like basically the points go towards inside as we keep on reducing the distance between z and a. So just it's okay. Just try to picture it as the function as z tends towards it, f of z also tends towards something basically. So now we get into the definition of the derivative. So can anybody tell me what the derivative is in the sense of real numbers? What do we really mean by f dash x? Can anybody speak out?
What I know is the slope.
Okay, that's the slope. That's actually a very good idea in the case of real numbers, in the case of the real nine. But it's kind of difficult to define a similar thing or bring the intuition here in the case of the complex plane. So, what is the limit definition that you see of the derivative? How do you define the derivative using limits?
It is
So you
oh, yeah.
Yeah, so what happens is that you take a very tiny chunk, means you extend x by a very tiny chunk, let it be delta x. So what you do
Okay,
is f of x plus del x minus f of x by del x is the
correct.
and del x tends to zero.
Yes, this is yes, this is the this intuition we can actually generalize in the case of complex numbers. This it might seem see the you might wonder why can't we come up with the concept of slope. There is actually a concept of slope even in the case of complex variable functions, but that is what you would call the gradient. Actually there are multiple ways to define it. You can look it up, gradient. There's also grad, div, curl. So there are these three concepts which come up a lot in IA. Oops, my pen kind of began malfunctioning. So there you can actually kind of
Okay,
define this.
if you
Yes,
see
yes, go ahead.
carefully that this formula is also a slope in some sense because you are just doing
Yes, yes, yes,
y.
that is
Yeah, but
correct.
if this is a slope in some sense, how is it different from the slope we do? Like, why are you telling it's difficult for complex plane while this is the intuition?
Okay, I
Like
mean,
it,
yeah, yeah, okay. So the reason why I'm saying is that I understand what you're saying. That's completely correct. In the case of it's actually what we call what I would call skill issue on our parts, as we live in 3 dimensions instead of 4 dimensions, right? So we can only we can the reason why we can visualize the slope is that we can plot the function on the y-axis as we like extend x, right? So we can plot it like this. But in the case of complex numbers, it's not so simple anymore, right? We would have to plot it in some sense in a 4D space because the input space is 2D, which is the complex plane, and the output space is also 2D, which is the complex plane. So that is the reason why it's kind of difficult
oh,
when you say, okay, right? So it's
yeah,
you can define it, and it is indeed possible, like with all these concepts as grad, div, curl, but it's kind of difficult when we're so what we're trying to do is that we are trying to see what happens in the real case and try to bring it back into the complex case. And here's the advantage of thinking about things abstractly in mathematics basically. So what we do is that okay, so I guess I won't be able to cover all the things as much as I wanted to in this class, but I guess it's kind of good that I am covering things in the way that people understands it and their concept and their foundations is good. So how we define the derivative of a function is this exact same thing. We define some delta z and we let it tend to 0, and we say f of z plus delta z minus f of z divided by delta z is as the derivative. So you might say, okay, so that was just very anticlimactic. So we can just do the same thing all over again, right? But here's the thing: what do we really mean by taking the limit in the case of the complex case, right? It's kind of subtle. Like for example, if I gave you the function z square, what is its derivative, right? It's not so simple anymore. Because in the real case, what we do is that we just add x plus some delta x and squared minus x squared by del x and see what happens to this as we send the limit to 0. But in the case of complex numbers, it's not so easy, and I'll tell you why. Let me just erase this. The reason why it's not so easy is that this complex number is actually some of this form, right? So when we say z plus delta z whole squared minus z squared, what we really mean is that x plus some delta x plus yi, um, yi plus some delta I squared minus x plus y squared divided by delta x plus delta y I. So here becomes the problem, right? Because we are sending both delta x and delta y to 0. So how do we really, like, it's not so obvious, right? We're sending both delta x to 0, we're sending both delta y to 0, and how do we send them to 0? Maybe we send delta x to 0 faster and then delta y. So it's really complicated. How do we do this, right? So once again, we look at what happens. So now I'm trying to get towards something called the Cauchy-Riemann equations. So it's a fancy name and it looks kind of fancy, but it's actually not. Um, by the way, is everybody clear with what I've said till now? Let me just check.
Yeah.
Okay, oops, somebody has. Um, okay, so Nikhil has been saying, why does it move like that? Could you like clarify in which context you're saying? It would be better if you could like speak out because I chat a
Yeah,
little bit.
he asked that out when he was saying that when the x tends to a point, then the derivative also tends to that point.
Oh, you mean the definition of the derivative, or which slide? Which slide?
Like if he was saying that when you from the z plane you are mapping it to another plane, then the
Yes, yes.
limit z tends to a f of z is equal to oh yeah, this one. Why does he's
Yeah.
asking why does it move like that?
Okay. Why does it move like that? You mean why have taken only these paths, or why the function is
Then
going to w0 like that, or
yeah, why is the function going to w0 when this xt is going to
here's the thing. Okay, so maybe I kind of explained this kind of badly. Okay, so maybe I should get back to limits a little bit. Okay, so those who are expecting some advanced stuff, I'm sorry. Okay, I'll just get this cleared with. So here's the thing. Oops. I No matter how we send z to a, maybe like this, maybe like this, like because the plane is 2D, we can send the z to a from all the directions. It can go from the backwards, from the right to the left, from the front. So no matter how we come towards a in the z plane, when we look at the w plane, f always goes to w, maybe in some different direction. But at the end of the day, no matter how we move z to a, no ma- f will always move towards w. That's the thing. So because the plane is 2D, it's kind of difficult because you can move the z around in a spiral. You can send it from the left to the right. So irrespective of how you do it, the f of z will always go to w0. So that is what it means when you say that um, limit of z tends to a of f of z is equal to w0. Does it make sense now? Nikhil, let me check the chat. It's kind of difficult at first when you're trying to wrap your concept around of a 2D thing, of a 2D behavior, because you can send z to the point a in multiple ways. You can send it to the from the right, from the left, from all directions. I'm not going and giving like the full rigorous definition, although I could give that. I'm trying to make you visualize and understand it, right? So Nikhil, if is that making sense, or um okay, so it's okay if you're not getting it, it's kind of fine. I would just say just go with the flow. Okay, maybe if you're seeing this for the first time, maybe I'm not explaining all the right concepts the right way. If you're kind of getting stuck at some points, it's okay. I'll just say try to capture the geometric, like the bigger picture nature of it and not get bogged down by the specific details, because analysis can be quite kind of painful that way. So now
Yeah, I
let's
think
get
not in the meeting anymore. He might have gotten logged out or something. We can just continue.
okay. Thank you, Sai, for pointing it out. Okay, so now we'll get into the heart of what it means for a function to be for a function to have to be able to be differentiable in the complex sense. So first things first, I will just point out this: if somebody is trying to impress you, all these definitions, holomorphic, conformal, analytic, all these terms, all of them mean complex differentiable. So if you're like reading up there, you're seeing, oh my god, this is holomorphic, oh my god, that's conformal, oh my, that's is analytic, they're all the same. So this is all their root definitions are kind of different in the context of complex analysis. These terms mean the same. Okay, so now we say a function is, so I've given the definition of the derivative in the in the context of complex numbers is this. But now we'll unpack what it really means. So let's say we look at the z plane and w plane. Okay, so w is just f of z. So we're just seeing what happens in a function when it gets mapped. Like we're trying to see what happens in fz. So let's say we take some point, let's say some point a. Okay,
Could you
and
just
let's say we just,
please
yes.
repeat the last 1 minute? Sorry.
I just defined what the limit is once again. I was just reiterating. Nothing special, basically.
Okay.
Okay. One thing that I said is that if like all these names, if a function is holomorphic, conformal, or analytic, all these three terms mean the same thing, with like some nuances in the in the context of complex numbers. They mean the function is differentiable, basically. So I'm just saying this because if you're reading some like Wikipedia or some like advanced textbook and you're like, oh my god, what is this holomorphic, conformal, analytic, what is this, I don't understand, what they basically mean is that the function is differentiable. Their root definitions are actually different. Like for example, the definition that I gave you of an open set, I gave you two definitions, although they're the same thing, right? So it's a bit like that. So don't worry about it. It's just some way of naming stuff, and don't get scared. These are all fancy names when they're actually kind of simple concepts. So now let's get back to the derivative. Um, so let's say we take a point A and we see what happens as we move some delta z to the right. Okay, so let's say we go to this point a dash. So what, now we look at what happens to f of z. So let's say f of z, f of a was over here. We now look what happens to f of a plus delta z. Okay, so now look at the displacement vector. Okay, so this is some I'm borrowing this concept from physics. It's not too difficult. Just look at what happens, like the arrow which is representing the change as we kind of shift the place at which we are currently. So as we move from a to a dash, we're looking at what happens of f of z, basically. So f of a goes from f of a plus delta z. Okay, so it's, so now what we do is that we now shift from a, instead of going to a dash, we go to some point a double dash. Okay, and let's say the displacement is some delta z double dash. And now what I'm going to say is that the absolute value of delta z is the same as delta z dash, or I've written delta z double dash there. So let's say we move, so what we're basically doing is that we're taking a point, we're moving towards the right by some small amount, by some small radius, and when we're going to the left by some, like in a slightly different direction by the same radius. So we are going in two different directions with the same radius, basically. So we look at what happens to f of a plus delta z dash in that case. So let's say it goes to somewhere here. So now, in order for this limit to be well defined, right? In order for this limit to be well defined, we must have that. Okay, I'll just erase this upper part. Um, in order for the derivative to be well defined, we must have that. Uh, we must have this identity to be true. F of a plus delta z minus f of a by delta z equal to f of a plus delta z double dash minus f of a divided by delta z double dash. Does this make sense? In order for the definition of the limit to be consistent or and make sense, we must have this to be true. Like just as I was explaining back in that slide over here, no matter how we go towards the point a, the limit tends towards the same thing. So this
Okay,
is
wait,
basically
wait.
the similar thing here.
Here, in
Okay.
that case, we
Right.
were going towards the point A, but here we are going away from the point A. How is that the same thing?
Okay, right. So, okay, that's a good thing that you pointed out. We are trying to send delta z equal to 0, right? So we are trying to make a dash and a double dash, both of them come closer towards a. Okay, this should not be equal. This should be approximately. Just to be clear, I was not being that rigorous. So, like, just imagine, like, as we are sending delta z and z double dash closer to 0, that is basically a dash and a double dash closer to a with the same radius basically. So this length and this length, like this length and this length equal, and as we keep on decreasing this length, right, we are looking at this ratios basically. And as we keep on moving a dash and a double dash towards a from two different paths, we look at what this ratio or this slope or whatever this derivative looks like. So in order for the concept of the derivative to make sense, these two should be roughly equal for some like real numbers delta z and delta z dash and in the limiting case these both should be equal. Does that make sense?
Uh, so like
Okay.
both of these are actually the different derivative of that f of a, right?
Yes.
So why are they not equal and why are they approximately equal?
uh then okay, so okay, let me just, okay, I'm just explaining it a little bit badly. Okay, let's just, they're approximately equal. They're equal in the limiting case, as delta z and delta z double dash, both of them go to 0. As they become as they go closer and closer to 0, this approximately sign becomes an equal to sign basically. Okay, so I'm kind of hand waving here because I'm not giving like the rigorous definitions, but I'm trying to give you the feel. In a moment, things will start getting a little bit more concrete. So let me just be specific, okay? Okay, so let me try to explain it this way. So let's say we have a function from z to w. Okay, and we look at what happens for some small delta z, right? And we want to know how delta f or f of z plus delta z, wait, let's say this point is f of z plus delta z. This is f of z. We want to understand how this ratio works, how this difference works, right? So approximately, like think about the real case, right? Approximately what we would want is that this to be equal to f dash z times delta z, right? Plus some, let's say some error terms, which like become negligible as delta z tends to 0. So this is what we really mean when we say, when we take the derivative or when we take the limit, right? So now what I'm trying to highlight is that, or stress upon is that, if we were to take another delta z dash in some like random direction, then also f of z plus delta z dash minus f of z, we would still have the same relation. Like this term here, like the slope term or whatever, or the way in which the delta z vector needs to be scaled so that it becomes the delta f vector. Like the scaling and rotating factor needs to be the same. That's what I'm trying to say. In order for the function, in order for this to make sense, or d by dz to make sense, or to or the derivative or the limit to exist, like this ratio should be the same. Does that make sense? So like irrespective of how we look at the displacements from z, like the ratio or the scaling factor, so this is what I'm trying to say basically. So like if we take a point z and we displace it slightly to the right or to the left, the ratio of f of z plus delta z minus fz divided by delta z, this ratio will be approximately the same, and in limiting case it is the same basically. Okay, so I guess I've kind of it's kind of difficult to truly understand what I'm saying when I say it like this. So let's get into some concrete calculations and see what I'm trying to say. So now I'll be deriving the Cauchy-Riemann equations. I'll just look at the chat if somebody has some doubts. By the way, Aryan, thus are you kind of getting what I'm trying to say?
Yeah.
Okay, Atharv is saying is conformal mapping theorem on the same idea, basically for holomorphic mappings. Do you mean the Riemann
Yeah,
mapping
like, no,
theorem
you're saying that
or what?
conformal and holomorphic and all of these things. So it's conformal mapping theorem basically on holomorphic mappings. It says that
That depends. Okay, I don't know which.
conformal mapping theorem
Okay,
is
so could you
basically like
specify what you mean?
the conformal mapping theorem basically says that if you have some two lines in the plane and you take some sort of mapping, then after that the angle between the two lines are preserved.
Okay, that's not that's not I don't know why you're calling it a theorem. That's actually the definition of a conformal map. It's an angle
Oh,
preserving map, right? So yeah, so what I'm trying, okay, so I was actually going to get to that basically, but you kind of went, okay, I guess you went and told me that. Okay, so now I'm going to get into Cauchy-Riemann equations. Okay, guys, now hold on tight, okay? So now we are going to do some really fun calculations, okay? So now, let's say we take a point z is equal to x plus iy, okay? So now we are really getting into the heart of calculating the derivative. Now all this has been like some philosophical kind of talk. Oh, like this as delta z is tending to zero, no matter from which direction, the ratio is remaining the same. You might be like, what are you trying to say? That's just like just saying something on the surface level. Let's just see what this means concretely. So
right, mom. Yeah, right.
Atharv, are you I think
Yeah,
okay, yeah.
and
Okay. So now what we're going to do is that we are taking a function fz, let's say, which is differentiable. See, I'm not being very overly rigorous here, and some things might not be correct in the strictest sense. I'm trying to give you the feel here, and then if we have time, I'll go into the concrete details. So let's say we have a function which is differentiable, complex differentiable. So now what we look is that we decompose this function f of z into some f of z is equal to u of x comma y plus v of x comma y I. So I'm just like decomposing the function into its real and complex parts, basically. And the function and the variable z itself into its complex and real parts. So what I'm trying to do using this way is try to imagine a vector field, basically. So like vector fields from physics, like electric field, magnetic field. So I'm trying to connect it to that. So don't get scared. Just bear with me. So now when we say f of z plus delta z minus f of z divided by delta z, let's expand this out, okay? So what does this really mean? This means that f of x plus iy plus um, plus delta x plus I delta y minus f of x plus iy. So now we are going to do something fun, okay? So now if we try to visualize it, right? So what are we doing? We are taking a point z and we're going to some point which is some dx over here or delta x here and going up delta y, right? So this is what we're doing when we're going z plus some delta z. We really mean we're going to the right by some small amount delta x and going up by some amount delta y. So now what does that translate into in the w plane? So we can think about it as taking the function, taking the point fz, then going to point fz plus some delta x, and then going up, right, to the point f of z plus delta x plus I delta y, right? So now what we can actually do is that we can decompose this roughly in a very, very rough sense. I'm not actually stating the theorem here. It's actually what I'm trying to get to is the concept of total differentiability in the case of multivariable calculus. So I'm not going to actually go into the exact details of it. But if you think about it intuitively, um, I'll just go to the next page.
Oh wait, can I just go to the previous page?
I haven't yet gotten to like the main thing.
Oh no, I'm just trying to understand what's going on in the W pool.
Okay, I'll just draw it a little bit better. My drawing skills are kind of bad. Okay, so I'll just explain it again. So here's the z plane, right? And when we say we are moving to some point delta z, moving by some delta z amount, what we really mean is that we're going to the right by some delta x and going up by some I delta y, right? Does that make sense?
I delta Y or
If
delta? Oh, I delta Y.
yeah, I mean, whatever. I mean, we are okay. So like the magnitude is delta y. Like I is just rotating it by 90 degrees. Does not matter in any case. So now if you look at what happens in the case of f, so f also, so we look at f of z and then we look at f of z plus some delta x, right? And when we go up and we look at f of some z plus delta x plus I delta y, right? So this is what we really mean by f of z plus some delta z, basically. So this is what we really mean. So what we can do is that we can, I'll just write it a little bit neater
Okay, wait.
because
We went. What? How much did we go up by?
we went up by f of z plus delta x. I haven't yet gotten to the main thing, right? We have
Okay.
gone to the right by this amount, and then we have gone up by f of z plus delta x plus I delta y minus f of z plus delta x. So if you add these two, you see, right, this cancels, this term cancels, and we get the normal difference, right? That I'm just trying to decompose the change as we're going by some delta z amount. We're going to the right by a little bit and up by a little bit. So that's what I'm trying to say. Does that make sense?
Yeah.
Okay. So now all this is not very rigorous, okay? Like if I have to make this rigorous, I would have to. It's not that I can't. It's just that making it rigorous requires lot of things which I need to get into, like defining total differentiability and all of that. If you're interested, look into it. So we can define this as the change in this is equal to change due to delta x, like change due to moving to the right by delta x plus change. Okay, I'm not specifying what I mean by change clearly here. like basically I'm trying to explain, I'm trying to do is I'm trying to decompose this. So now just hold on tight. So now what does change due to delta x mean, right? It means change, okay, change in f, I should write change in f. Uh, like I'm trying to understand what happens if we, how does f change by moving z to z plus delta x. So if we decompose f into its components u and iv, right? So we can think of it as delta u by delta x plus I delta v by delta x times delta x, where if you've forgotten what u and v are, I'm just defining f of z as u of x comma y plus I of v comma v of x comma y, basically. So that's what I'm just decomposing the function, right? And now similarly, the change due to y, change in f due to delta y is nothing but delta u plus by delta y plus I delta u delta v by why is my handwriting so bad, right? Does this make sense so far? Like all this is roughly correct. I'll get to the exact formula in a moment, but does this make sense so far? I guess if somebody has any questions, you can put it in the chat. Okay, so I assume you don't have any questions, so I'll just keep going forward. Once again, feel free to interrupt me if I'm speaking. So what does that mean? So f of x plus y plus I by um, plus delta x plus I delta y minus f of x comma y. And now when we are looking at the limit, right? This is the limit. So we can write it out explicitly as delta u by delta x plus I delta v by delta x times delta x. Okay, this is all like very unrigorous the way I'm writing it. So delta basically means change. If that is not clear, if to somebody, delta basically means change, like change as we are changing x, change as we're changing y. So we are basically going to get to a concept which is very similar to the derivative. And this is just f dash z, right? So what do we want? We want this expression, right? We want this expression to be to be a complex number, right? We want this to be some complex number. Okay, let me just clarify what I mean. We want the numerator here, we want to be able to express the numerator here as as this some complex number f dash z times delta x plus I delta y, so that when we expand it out, it cancels out with this. So I'll just write it in the next page. What we want is that the numerator from this expression, wait, I'll just put it here actually because it's kind of, so what we want is that the numerator to be approximately equal to some complex number f dash z, which is like independent of delta x and delta y, which is the key thing here. It's only dependent on z and not delta x and delta y, so that when we write it out, this and this will cancel, right? So we want this to happen. So we need to now figure out, when does this above expression factor out nicely in the form of some complex number, right? So so now I'm going to do some kind of black magic and some experiments to see if we can Okay, very sorry people. I kind of got disconnected. Um, if somebody could like point out till where I had covered, it would be kind of nice. Before I got disconnected in the chat. Uh, I'll just share my screen. Could somebody confirm that you can hear me?
Yeah, you're audible.
Yes.
Okay. Mandar, did you see me cover this? Like talk about that x plus I y as a column vector.
No, we haven't reached that.
Okay, okay. But did I
Yeah, you covered this part.
the canceling part? Did I cover?
Yeah, like you explained, key. We need something. When does this cancel? Like, why do we need it to know when it cancels? And
Okay,
the
okay,
like
okay,
worked
okay,
about roughly.
okay, okay. So now, okay, I'm happy that people are following along. Okay, so now here's the black magic part. Okay, so this is going to be really fun if you're seeing this for the first time. So what we do is that we look at this complex number z is equal to x plus iy, and we represent this as this vector or this matrix, right? As this column matrix x as x comma y. Why am I looking at it like this? Well, if you look at if you add two complex numbers, right? That's kind of the same like adding complex numbers. You add the real parts and then you add the imaginary parts, which is kind of similar to what you do when you add these matrices, right? You add the first row, then the second row. So what you get is x plus x dash, y plus y dash. So I'm trying to use a similar structure. So what I'm going to do is that this expression here, I'm just going to drag this out. Wait, because this is an important expression. Uh, oh yeah, why is this not working? I'm just going to copy this expression and write this out in the form of a vector. Okay. Wait, actually though, wait, I'll just move this a little bit up over here so that it looks nice. So now what I'm going to do is that I'm going to write it like this. I'm going to represent the change in the form of this vector and write down the whole expression the form of in the form of a matrix. So if it's kind of confusing, I'll just bear with me for a moment. I'm not um, I'm not going to be, wait, just give me a moment. I have to be kind of careful about how I do this. Ooh, it should be delta x, delta, yeah, it should be this. Okay, so so we are going to, we're expressing this because, and why are we looking at this? Wait, what the heck? If you expand this out, what you get is this expression basically, delta u by delta x times delta x plus delta u okay. So we get this expression, which is, and if you look, the column just represents the real change, like the real part of the change, the real part of this expression, and this basically represents the imaginary part of this expression, right? So I'm just doing this trick of like expressing this in the form of a matrix. And now here comes the black magic. When does, if we represent xy as the same thing as the vector x plus iy, when does multiplying this vector by some matrix ABCD become the same as multiplying x plus iy with some complex number z? When does matrix multiplication start behaving as complex number multiplication? So let's see. Let's take the complex number x plus iy, and let's multiply it with some complex number a plus ib. So what happens is that we get ax minus by as the real part, and the imaginary part is ay plus bx, right? So this is what we get, like I should put an I here. So now if we were to express this in the form of a matrix, we would have xy, right, multiplied with, maybe I should write out the multiplication in the opposite sign so that it's uh, kind of easier for you to follow that which is acting on what. I, I can't even select this, which is so much skill issue. Okay. Okay. So now just bear with me. So if we write it out in the form of a matrix, what we have is that we have A minus B, the real part, right? When we multiply the matrix, and over here what we have is B and A. So basically, whenever we're multiplying a complex number with another complex number, like the corresponding 2 by 2 matrix must be of this form, basically. A minus B, B, A. And so now this matrix, right? This matrix should correspond to a complex number in order for the definition of a complex derivative to make sense. And in order for that to be true, oops, that's not the correct matrix. In order for this, we need this matrix in order to be able to represent a complex number, so that when we multiply it out, we get that f dash z times delta x plus iy. So this number basically should represent a complex number, if that makes sense. So now what does that mean? If we copy this matrix here, um, what we have is delta u delta x, delta u by delta y, delta v delta x, delta v. Is this correct? Or am I missing something? Let me just think about it. Wait. Delta u delta x delta v. Okay. Okay, that's correct. So what does that mean? If we what that means is that this and this must be equal, right? And this, like I'll just write it a little bit cleaner. This and this. So these two terms must be equal, and these two terms must be opposite. So what we have is delta u by delta x is equal to delta v by delta y, and delta u by delta y is equal to minus delta v by delta x. Does this make sense? So if anybody has any questions, you can kind of point it out. Like, does this derivation make sense? If some part is not clear, I can like reiterate it. Okay, so I assume that it is making sense. Okay, so now these equations are nothing but the Cauchy-Riemann equations. Okay, so now to use some fancy notation, so now we'll write delta u by delta x as what is this? We denote this use as using this symbol. So what this basically means is that the change in u by only changing x, as u is actually a function of x and y. When we write delta u by delta x, we only mean what we really mean is the change in u due to the change in delta x, not any change in delta y. So x and y are independent, and we are seeing what happens, how delta u changes when as we change x and keeping y fixed. So if we write if we do that, what we get is that delta u by delta x is equal to we get these equations basically. um so these equations are the famous and like world renowned Cauchy-Riemann equations. So as you just saw, these are really not that uh, that that much of a sophisticated idea. It's just just seeing how the function changes due to x and y, writing it down, and ensuring that that the definition is consistent with the definition of limits. We impose these constraints on the matrix that we constructed, and we get these equations out. Okay, so now I guess I've got to an important part of this class. So now so now we've got like a really nice condition, a much more practical condition on what it really means for a function to be complex differentiable. So to specify the whole, to just recap what we've got in here. Okay, so there are some small subtleties to this, but like I'm not giving the exact condition. There's also, like, if you read the exact criteria, you will see that the function fz is totally differentiable in the real sense. This is also an exact also a criteria, but I'm just not writing it because I haven't defined what it really means, and you should not be worried about it that much, because I'm really trying to capture the geometric idea of these ideas. So this is really the fun thing. Okay, so now there's a really nice way to interpret analytic functions in the in the sense of a vector field. Okay, so what is really a vector field? A vector field is basically a field which assigns a vector to every point in the plane or the space or whatever. Okay, this is not really mathematically rigorous, but I guess it works. So I'll just, for example, I don't know, like the electric field, where which is, let's say we take a charge and like the electric field is pointing out, so that's a three-dimensional field. So in this case we're going to be working with two-dimensional fields. The reason why I'm pointing out this concept of vector field is that if you take a function of this form, these complex functions, these complex variable functions, these are actually vector fields if you think about it, because you can actually represent this as this, right? You can represent them in the form of some vectors. And the reason why and the cool thing is that you can actually make plots of these functions. For example, you can take some f of z and you can actually plot it out. For example, if we take the real plane and if we plot fz is equal to z, what we get is just this, like just radially pointing out arrows, and the size of the arrows basically keep on increasing as we go away from the origin, basically. So we can think of these complex variable functions as vector fields, and the reason why they're so fun is that you can do a lot of interesting things out of them. Okay, so here's some really fun, like the truly fun properties of analytic functions come out when we start doing integrals on them. For example, um, if we take a function. Okay, so before we get into actually integrating functions, I think I should actually specify what I mean by integrating a function over the complex plane, right? It's not as simple. So if somebody is willing to, can somebody just tell me how do you integrate functions in the real plane, or in the real line? If somebody is willing to. We're just going to take that definition and try to extract as much out of it and try to put it onto the complex, in the case of complex numbers. So if anybody's feeling free, I don't need any like very rigorous definition, just like the idea of it. Okay, so seriously guys, come on, somebody. All of you one of you should know this, right? Like of course many of you know, but I guess you're all shy to point it out.
Like we just approximate the area with rectangles and then make rectangles very small.
Yes. Okay, that's all I need. It's not this is not rocket science. It's just that, right? We take the function and we look at rectangles, right? When we Okay, I'm drawing it really badly. So when we're looking at some fx dx, what we really mean is that we're taking the sum. Okay, not okay. Don't look. Whenever I write equal to sign, chat, it actually means approximately, because wherever I write equal to, it either means there's a limit going on some supremum, infimum, some like weird nonsense is going on. I'm not going to write that out, and that really does not contribute that much into like the feel or the intuition of the subject. So what this really means is that we are taking rectangles of height f of xi and some width delta xi. But once again, in the case of complex variable functions, we can't exactly do that because we can't visualize functions. We visualize stuff in the 4D. So what we're going to do is that we're going to try to look at this and try to work it out. So what we're going to do is that, okay, let's say we have, once again, we look at the z plane, right? And the w equal to f of z plane. So what we're going to do is that we, in the case of real numbers, we usually integrate over an interval a comma b, right? So we take some point a, some point b, and just integrate over this as the function exists here. So like we just keep drawing rectangles and just approximate and refine the approximation and try to understand it. In the case of complex numbers, we really do not have the same thing as an interval anymore. So what we do is that we define integrals over paths. So what we do is that we take a point A and a point B, and we draw the loop around it, or draw a line, or it can be a line, it can be a curve, it can be anything. So whenever we are taking the integral of a function, what we really mean is that we're taking it over some loop. Let's call this loop L. So we are taking it over a loop. So that's the first thing. And how do we really define taking the integral of a function over a loop? Well, we try to rephrase it in the case of real numbers, basically. So what we do is that,
Wait, but why loops? Like,
okay, not loops. Okay, some path, basically. I shouldn't have said loop. Loops are interesting. I should say path. See, like, okay, I'll just say this thing, then you can continue asking me.
sure.
See, in the case of an interval, you can only go from a to b, right? It's just one line. Like, you can't go to the left or right, you can just go straight from a to b. But when you have a plane, you can go up, down, left, right. As long as you end up at b, that's kind of the same thing. In the case of intervals, you might say, oh, okay, I can go along the positive x-axis and then go back, right? So like, let's say, you could say like this, that okay, so this is a, this is b, and okay, so maybe you are going from a to some a dash, you keep on integrating till a dash, and then you go back somehow to some point, some b dash, and then go back to b. But if you think about it, if you know some little bit calculus, you'll know that it eventually evaluates out to just directly integrating it from a to b, right? But in the case of complex numbers, right? The case of complex numbers, there is really no sense of, okay, from a to b there is only one path. There are multiple paths. You can go to left, right, up, down. So hence, whenever we're defining an integral, we look at what happens across the path, not across one particular path. Okay, if does that make sense, Mandar?
Yeah, so like we just integrate over a random case. Not a random case, but over all the possibilities.
No, we don't. So no, it's not over all the random cases. We define the integral over a specific path. Like in the other case, we define the integral over the interval. Do we define the
Okay,
integral?
sure. Like, yeah, like you mean to say, okay, I got it. Like you just first specify a path and then integrate.
Yes, that's just, it's not that complicated.
Yeah.
Although, as we will see in the case of analytic functions, under some criteria, the integral is path independent actually. So like, it does not matter which path you integrate along. I just kind of spoiled it there, but okay. So now, what do we really mean by integrating over a path? So we'll be only looking at paths which are sufficiently smooth. So like, we can we look at when we can basically parameterize this path, right? L, with some parameter t. So let's say L of 0 gives the point A, L of 1 gives the point B, and L of t, where A is the initial and B is the final point, and L of t gives some point t, some point, like let's say C, along the path. So what we're assuming is that we can characterize the path with some nice function which is kind of smooth, you can differentiate it. And so when we mean that we're integrating f of z dz, what we really mean is that we're integrating f of this path LT times L dash T times dt. Because if you think about it, L dash T dt is nothing but dz, right? Because if we are going from here to here by some small amount dz, that is just lt plus some delta t minus lt, and now you just divide the whole thing by delta t and multiply it by delta t. Okay, so that is kind of unrigorous, but you kind of get the idea. So we're going to define fz dz over a path L as this integral. So what this why this is so helpful is that when we say f of z dz over the path L as this, why is it getting tilted all of a sudden? When we really mean this from 0 to 1, we're converting the path integral into one variable integral, basically. So we're just trying to capture the thing from in the case of real numbers, and we're trying to force that into on the complex case, basically. And here's the reason why complex numbers are so interesting. As I leaked it before, if a function is complex differentiable on okay, maybe I should okay, this is kind of small place for this. I'll just how do I I'll just go to the next page. Okay, so here the definition of open sets come into play. If a function fz is okay, I'm not telling what simply connected means. So, or it's like there are like, let me just remove it. Actually, there are a lot of kinds of domains where you can do this. So just think of them as like sufficiently nice domains with no holes, so as to say. So I'm just going to remove this all altogether. So if a function on open sets which are nice, I'll just write it like this: integral fz, let's say, on a path L, which uh, so so here L and L dash are basically two paths which start and end at the same point, basically. So if this is L and this is L dash, this integral, if I should put a dz also, because yeah, so this integral, if the function is differentiable, then this integral is actually path independent. So this is the reason why these analytic functions are so fun to work with. And now I'll give a really fun geometric proof of this statement, basically. So now let's try to unpack this, right? When does the integral, wait, I'll just look at the chat because somebody might have asked something. Okay. Somebody might, okay, so nobody's asked anything yet. Okay, so I guess I should say this, and I should probably end this. I should probably not go on much more longer. So what does it mean? Right? So here's the thing. Here we're going to do a trick, okay? So let's say we have 2 points A, B, and we integrate along this path, right? L, and because the integrals are path independent, this integral I1 and this integral I2 are the same, right? I1 is equal to I2. So now what I'm going to do is that I'm going to write I1 minus I2 is equal to 0. And what does minus I2 mean, right? What does minus I2 mean? Just means that instead of taking the integral one way, we are taking the integral in the opposite direction. Okay? Does that make sense? So like in the first case, when we were integrating it in the normal sense, we were going from A to B, this direction. So minus I2 means that you're taking the integral from the opposite direction. It's just like in the real case when you, instead of integrating in the interval from A to B, you're integrating from B to A. So that's what I'm doing. It's not like really complicated. And what does I1, I2 as a whole mean then? It means that you're integrating from this and then turning around and going back to A, right? So you're going along this, and if you go back along, it's just this loop integral along this loop, right? You're going from A to B and then B to A, and this must equal 0. So this is the key thing. So we can actually write this down actually. This is much more of a compact way of saying this. Integrals of differentiable functions along loops is equal to 0. And there is actually, we can really prove this in a much more nicer and cleaner geometric sense. So what we do is that we take the complex conjugate of wait, just give me a moment about how to do this, because there's some subtlety about how we do this. Just give me a moment. Just okay, so here's what we're going to do, okay? What we're going to do is that we're going to take the complex conjugate of this expression, okay? And we're going to look at what happens as we're going to try to prove this, okay? So do you see why these two are kind of related? If we prove this, we get that. Because what happens is that if you take the complex conjugate of this, the complex conjugate kind of distributes out to the dz, and then we just flip the sign for it basically. So just don't worry about it that much. So what we're going to do is that we're going to prove this statement instead. And there's a really nice geometric way to prove this expression actually. So what we do is that once again, we write the whole thing out. We have u plus iv complex conjugate dx plus I dy. And if you expand this, what we get is that integral of u dx plus v dy just what am I doing actually? Am I messing it up? Just give me a moment. Okay, I think I'm doing it correctly. We have this expression right here. And now
Wait, shouldn't it be udx minus vdy?
right, sorry.
And like udy plus vdx, unless.
Okay, yeah, I got the signs mixed up, did I? No, I'm taking a complex conjugate. Did you see that? Or wait, am I messing it up? Wait, udx plus like the I and like if okay, let me just write it out explicitly. So I'm looking at the complex conjugate instead
Oh.
of the function itself. So
Okay, okay.
that's
I missed that. Sorry.
yeah, okay. Okay, so I actually need to revisit this argument a bit myself, but I'll just get the point across. So now if you look at this expression here, what we have is u dy minus v dx. And there's actually a nice way to interpret this integral, okay? There's a nice way to interpret this. Actually, the y, wait, just give me a moment. What am I doing? dy y del dot. Okay, guys, very sorry, guys. I should not be. I'm actually clowning right now. Oops. Very sorry. Very sorry. I kind of got the argument messed up myself. Oops. Sorry. I should not be looking at the complex conjugate here. I'm really sorry. You can't actually do this. I'm really sorry. Really sorry, guys. We are looking at this function itself. Okay, so we'll be proving this statement. Really sorry. So I'll just expand this out. Really sorry. So what we have is integral of u dx minus v dy plus um, u dy. Wait, what is happening here? Yeah, v d. Okay, just give me a moment, chat. I messed this argument up. Just give me a moment.
I mean, you can look it up if you're not sure.
Yeah, it's okay. I should probably or should I go with another argument actually? Just give me a moment. I'm just trying to remember it. Just really sorry. Really sorry, guys. Just let me think for a moment. Okay, I got the argument. It's not exactly how I wanted it to be, but okay. But okay. It is what it is. So we expand this out. Okay, we try to look at this expression here. Is this correct? Just I think this is correct. Okay, so we try to look at this expression. So here we are going to do another fun trick. Okay, so we are going to try to interpret this f as a vector field. Like I was saying, interpreting f as a vector field is kind of a really cool idea. So now here's the thing. Look at the vector field. Let's define the vector field big F as u minus v. So this vector field is basically like uh, the vector field corresponding to the complex conjugate, right? We're just make instead of looking at the vector field uv, we are looking at u minus v. So we are trying to look at the complex conjugate. So here, this is where I made the mistake. Actually, really sorry. And there's this really fun thing. What we can do is that we can write out u dx minus v dy as a dot product, basically. So we can write it out as right. Does this make sense? We're taking the dot product or the matrix product of these two matrices, or maybe I should put square brackets because That's what convention that I've been following. So we're looking at the dot product of these quantities. And here's the thing, there's this really cool theorem which allows us to evaluate vector fields of this form. If you think from physics, like if you think about work energy theorem and all that, you will know that if you have a conservative force and if you do work, if you do work with that conservative force around a closed loop, the net work done is zero. So basically I'm trying to do that here. So what I'm trying to do is this part u dx minus v dy. I'm trying to interpret this as work done by the vector field u minus v. And if you actually check the math, like the criteria for when a vector field, like when the loop integral around a vector field or the work done around in a loop by a vector field is zero, you will actually see that this expression actually satisfies that. The equation for checking whether a vector field v whether the whether the hmm, wait, I'm just kind of so like basically what I'm trying to get to is that if you try to interpret this as work done, what you will see is that this expression actually evaluates to zero. So if you look at these interesting vector fields which are generated while trying to do these integrals around this, like these expressions, if you look at the vector fields u minus v and v comma u, the work done so here is this really cool way to try to understand this. So I did not actually go into the exact details of why this expression, why these actually loop integrals and why this work done actually vanishes. But here is this like really cool way to interpret this expression as work done basically. And you can actually I'm not exactly sure how to evaluate this and how to get these integrals done right now because I think I might be messing up something. But basically this evaluates out to zero, and that's a really cool way to think about analytic functions. Um, and another thing that I wanted to finally point out, okay, Gulshan Kumar thinks is saying that he was thinking of the exactly the same thing. Okay, that's kind of the way. Okay, I should probably look this up and get back to you guys because this was really bad. I should have known this by heart. Another interesting property of these analytic functions, when you look at how integrals work, is that you can actually express the derivatives of a function, of an analytic function, in terms of integrals of it. So what do I really mean by that? I'll just finish it off with this topic here. I guess my class is going on for a little bit extra. Let's look at the integral of the function 1 by z dz, right? And this function, if you actually evaluate this, you might say, okay, this should evaluate out to zero because 1 by z is analytic. Well, here's the catch. Because 1 by z is actually not analytic at zero, this integral actually does not this integral does not actually evaluate out to zero because it is not analytic at zero. It actually blows up, and this is a really interesting thing about these functions, like these analytic functions which are analytic over open sets, but start behaving, just begin blowing up at like special points, and these points are called poles basically. So let me just clarify. Okay, so there are some subtleties into this definition. So we'll be now investigating how these poles work. So now if you look at the loop integral of 1 by z dz, like basically if you take the plane and if you take a loop around this unit circle, which is, let's say this is 1, this is I, what happens is that this integral actually evaluates out to, I believe, 2 pi I. This is a really fun exercise to like test out yourself. So it is interesting to see what happens when you have these analytic functions which are analytic at all points except for at these special points called poles. And the interesting thing is that now I'm just going to start just telling some like really fun facts and not going too much of the proofs. This is one of Cauchy's theorems. So there's this really nice theorem by Cauchy which actually allows us to express the properties of function, like the analytic functions, in terms of an integral. So you might say, okay, why is this so special? How does this really shine light into anything? So why does this? So what we see here is that differentiable functions have this really nice sense of rigidity to them. This kind of averaging property, okay, I should probably put a dz around this, has this really nice averaging property of it. So like if you think about it this way, if you try to average around take the average of a differentiable or an analytic function around a specific loop, then you actually get the function, you you actually get the value of the function at the center of the loop basically. So like when I say loop here, I mean loop centered at A. And the reason why this is so special is that we can actually express the derivatives of analytic functions in terms of an integral. So I'm just going to do some weird maths which might not seem as, which you may or may not know. I'm going to use what is called the Leibniz theorem. And I'm going to pass the derivative within the integral. Actually, and when we're evaluating this derivative, we're actually looking at the change as we're varying a and keeping, like, once we enter the integral, we're not looking, like when we look at the integrand, we're no longer looking at how z itself changes when we're evaluating this integral. So we can actually make this derivative is actually a partial derivative. So in any case, it does not matter. You can think of it as normal derivative. And if you evaluate this out, you get 1 by z minus a squared. So what you basically get is that you can express, just to clean things up, we can basically express the derivative of the function in terms of the integral of a function because of this fun, really nice analytic property of it. And as a consequence, what we see is that by the way, just to be clear, once again to reiterate the point, differentiable and analytic functions are the same thing, like in the context of the context of complex analysis. So this is one really fun property about functions in the complex plane. This only holds in the complex plane, by the way. If a function is complex differentiable once, it is complex differentiable multiple times, exactly because of this. Because we can express the function in terms of its integral, and we can differentiate the expression to get this really cool expression. And observe that we can express the derivative of the function in terms of an integral of the function. And because of that, because if a differentiable function is differentiable at, just like borrowing the idea from induction, if a function is differentiable once, we can differentiate it twice, we can differentiate it thrice, we can differentiate it infinitely many times. So on in other words, if a complex variable function is differentiable once, it's infinitely differentiable, which is a really cool property of it. And finally, so like this is some really cool thing that I like to point out. And finally, as I had said at the beginning of the class, that there is a really nice connections between analytic functions and electrostatics, right? So if that is the reason why you are here in this class, I'll just point out this really another fun connection between analytic functions and electrostatics, which is that. So what do I mean by this? I'll just create another slide. So what this really means is that if you observe the real and imaginary parts of a complex variable function, they obey the same equation, or in fact the similar equation, as the vector potential, sorry, the scalar potential does in the case of electrostatics. For example, many of you might know this equation, which is the I don't know, is it called the Laplace equation or the Poisson equation? So the Laplace equation states that. Okay, maybe I should clarify here, because not a charge-free system, in which case it's actually the electrostatic potential is zero. Charge-free region. The electrostatic potential satisfies this equation here, where V is the electrostatic potential. And if you actually, here's the interesting thing. The same property is actually satisfied by the real part and the imaginary part of a complex variable function. And how do you prove this? So those who don't know what this del square means, this symbol, I'll just clarify in a moment. Del square is basically this function. Okay, so del square V basically means this expression right here. And if you do the same thing, if you compute this expression right here, um, did I write this? Okay. What you will see is that, like, if I use the previous notation and write real part of f as u, then if you just expand this out, what you get is that partial u partial x is just um, and if you expand the other part out, you get the minus of, if you actually go back to the Cauchy-Riemann equations, which was somewhere here, plugging this expression in, and here's the, and using like this very famous theorem from like from multivariable functions, you can actually swap these partial symbols, like well, partial derivative symbols, so you can actually write this out as I'll just you see that these expressions are the same and they cancel. And the reason why this is so fun is that I'm just going to end the class here. Uh, how do I do this? The reason this is so fun is that if, let's say, you want to solve for the electrostatic potential in a let's say a random geometry, let's say it looks like this. Okay, maybe okay, so we assume that the z derivative is equal to 0, so okay, there are some subtleties into this. Let's say we want to solve the electrostatic potential in the case of some weird geometry like this. What we can actually do is that we can solve it for a nice geometry like a rectangle and map it onto this using these analytic functions. And the Riemann mapping theorem actually tells us that okay, so once again, there are some criteria on what kind of open sets they are. Like they cannot stretch to infinity and stuff. Conformal, that is a differentiable function. So this really highlights like the power and like the niceness of these analytic differentiable and conformal functions. And like I will stop the presentation now because it's like half an hour overdue. Okay, I will send this PowerPoint in Discord, and I will actually correct my proof of the loop integral thing because I kind of botched that. Apart from that, I guess I kind of got everything else right. Uh, what I really wanted to highlight in this class is that these complex differentiable functions or analytic functions or whatever you call them, they're really nicely behaved. Like they satisfy like really some fun properties, like some really fun averaging properties. Like if you look at their maxima, minima, their integrals, you can analyze the properties of various loops, etc., etc. So and this is a stark contrast from real analysis where all functions have this really weird properties. Like you can end up with really weird pathological functions, like functions which are once differentiable but not twice differentiable, functions which are continuous but nowhere differentiable. These kinds of problems just kind of melt away when we go into one higher dimension. And the thing is that it only these kinds of properties like the Riemann mapping theorem and all these things, these only apply for the 2D case. They really don't apply for higher geometries, which really makes complex numbers a much more richer and interesting domain to work in, basically. So I guess that's pretty much it. Um, so yeah.
Yeah.
So if you
Thanks, Yash. That was a great class.
Okay, I kind
Yeah,
of messed up the loop integral kind of derivation there. I don't know how I forgot the
nah,
proof.
yeah, yeah, that happens. That happens.
So
So
I'll
wait,
write up the proper proof of it. I mean, I thought the whole proof was in my head. Like I don't know how I forgot it. Okay.
mhm.
So
Wait.
like
Also, if I want to read about complex analysis, what do you
oh
do?
s- so there's this really good book by Tristan Needham which is called Visual Complex Analysis. It's not really rigorous, but it kind of carries the same. I kind of was really inspired from that book. Although I took some parts from other textbooks as well, like the concept of open set. Like there are basically quite a few good books. You can look at Apostol, you can look at Tristan's book, and then you can look at there's this book. You can look this up. Why is it getting blurred? It's complex analysis by I'll put it up on Discord. It's Analysis by Freitag and Busam. That's also quite a good book, but it's like really terse, and you need to like every line is like packed with information you cannot misread or ignore any line. Basically, you have to be very careful. It's not very thick book, but it contains a lot basically. So yeah.
Mhm. I see.
Wait, won't
Uh,
napkin have it as well?
Napkin also has it, but like you can look at napkin as well. Like some others have looked at it, but I myself like napkin has like some other stuff like meromorphic functions and stuff, but napkin does not really go into that much depth. And you like if you want an overview, nice overview, you can look at napkin. Napkin is like as a broad overview of math, it's really good. But if you really want to appreciate the appreciate complex analysis specifically, like understand the geometric flavor of it particularly, I would recommend like looking at visual complex analysis. There's also this book by Sergey Lang that I have over here. It is also a really good book. It's just that I don't understand, like my style does not really match that well with that book, but you can look at that. That's also really good. I borrowed the definition of open set from this book basically. So yeah.
Mhm.
um Wait, how do I turn off the recording actually, or will the recording stop?
It's like there's a button for recording there, like in the lower panel, assuming you are the co-host.
um okay, let me just see if I can.
Yeah, you are the host, so like there is a recording button there. You can just click and stop it.